Hello everyone, I am Mathieu Vavrille, and today I will be showing you a work I did during my PhD with Charlotte Truchet and Charles Prud'Homme about solution sampling with random table constraints. So, solution sampling is the problem of returning a solution randomly and uniformly. This is notably useful to have a user feedback, for example, in dynamic modeling, because you won't have deterministic solution with random solutions. It's also useful to have equity, for example, in planification, because there won't be solving bias induced by a search strategy in the solver. And it's also useful to have coverage of the solution, for example, for automatic generation of test programs, because the solutions you will get are representative of the solution set of the model. My contribution here is an algorithm to sample solutions that is inspired by the work of Kuldeep Singh Mill and his PhD. But here I'm interested in table constraints. I will be adding table constraints to the model, and I'm using a CP solver as a black box. As long as your CP solver can deal with table constraints, you will be able to apply my approach to your model. And experimentally, I implemented my approach in Java using the solver Choco solver, and I show that there is an improvement of the randomness compared to random Prud'Homme, and that the running time stays in the same order of magnitude, which is very great because we ensure more properties. First, I need to show you how to generate random table constraints. So we have two parameters. First, the number of variables, v, and then the probability to keep a tuple, p. In this example, we have 4 variables, and we choose a probability of 1/2. So to generate the random table constraints, we enumerate all the tuples for these 4 variables, and you keep each of them with probability 1/2. So here, we keep all the green ones, and they will be part of solutions, and we remove all the red ones, and that will remove solutions. Why we generate these random tables is because we want to reduce the space, the search space and the solution space. And this is the property shown in the last blue block. So if you have a CSP and you add a random table generated with probability p, then on average, you will reduce the number of solutions by a factor p. That's what we're interested in, because we can't enumerate all the solutions, so we have to reduce the search space. Now, the sampling algorithm, we first have to choose a third parameter, which will be a pivot value, kappa, and we rely on a function, find solutions, that will make call to the CP solver to enumerate at most kappa solutions. So the property of this function is that if it returns kappa solutions, it means that there is more probably than kappa solutions remaining in the model. But if this function returns less than kappa solutions, we know that all the solutions, all the remaining solutions have been returned. We have this function because we can't enumerate all the solution space. For example, I will have a problem where there is more than 10 to the 12 solutions. So it's not decently possible to generate all the solutions. So we have to reduce ourselves to a maximum given number of solutions. And what we do to achieve this number is that we will add table constraints to reduce the number of solutions in the model. I will be using this figure, so it's a representation of the search space, and the triangles are the solutions. To show you the algorithm is written here in pseudocode, and I'll take an example with kappa equals 4. So first, we just do a first step, we find solutions, and if there is no solution, we just stop it because there's no interest in sampling an unsatisfiable model. Then we add a random table. This reduces the set of all solutions. Then we ask the function find solutions. We ask at most 4 solutions. So here it finds 4 solutions. It means that there is still more than 4 solutions. So we add the table. We generate a new table. We find 4 solutions. We see that there is still 4 solutions. So we know there is more than 4 solutions in the full solution set. We have to keep going. We add a new table. And then we see that we made the problem unsatisfiable. So here we just don't add this table to our model. We remove it. We generate a new random table, which on average won't be the same. We enumerate at most 4 solutions. Here we see that it returns 3 solutions. It means that we enumerated all the remaining solutions. And we can now return a random element from these 3 solutions. You can have improvements of this algorithm, small improvements. For example, here you can add on line 6 a propagate step before the generation of the random tables that allows to remove some values in the domains of the variables that would be immediately removed in the propagation step. So we don't want to put them in the tables. And another improvement is the dichotomic addition of tables. So here it's a little bit more involved. The idea is to add at each step twice more tables than the previous step. So instead of generating only one table, here we will generate k tables, and we will check how many solutions there are with these k tables. If there is still solutions, we add these tables to the problem. Actually, it's a little bit more complicated, so we have to deal with the fact when we made the problem inconsistent, but you can find all the explanation written in the article. So now, about the implementation. We implemented our approach in Java using the solver Choco solver, and we used instances of different real-life problems. So we have on-call roosting, which models a planification problem. We have feature models, and we have Renault-Megane configuration problem, which are configuration problems, and we have the n-queens, that is a toy problem. These 4 problems show really different properties. For example, on-call roosting is a very sparse problem. Renault-Megane configuration problem has a lot of solutions and is very dense. And the n-queens is very structured problem. Now, what do we compare to? We compare to the random search strategy, which is random Vardom, which at the decision step, it randomly chooses a variable x that is not instantiated and a value small x in its domain and makes the decision x equals small x. Sadly, this simple strategy is not uniform, so the solution sampling will not be uniform. And on this example, with 2 variables that are binary and just 1 constraint, the 3 solutions will not have the same probability to be picked. So the 2 solutions where x is different than y will have probability 3/8, and the solutions with x equal 1 and y equal 1 will have probability 1/4, versus what we want would be to have every probability at 1/3. So now, how to evaluate the approach? We have randomness in our approach, and that's very hard to evaluate, so we do it experimentally. So we need to evaluate the impact of the parameters of my approach, and we have to evaluate versus random Vardom. And what will we evaluate on? We look at the quality of the randomness, so how far are we from the uniform distribution, and the running time. So the results that I will show you here is that my approach shows better randomness, but as random Vardom, there is still no uniformity guarantee, and we show that there is a reasonable running time. Even though we have more properties, we have a better randomness. So here I plotted a graph where I show the p-value depending on the number of samples done. So the p-value is a quantitative measure of the distance to the uniform distribution. So the lower the p-value, the further we are from the uniform distribution. When increasing the number of samples, we see that we diverge more and more from the uniform solution. We diverge more and more from the uniform distribution. But what we see is that random Vardom, which is here in blue, you can do way less samples than table sampling, which is here in shades of red. But for example, with the parameters v equals 5, you can do way more samples with the same distance from the uniform. So it shows that we really have an improved randomness by using table sampling. And here I also show that when increasing the number of variables, so when the red is getting darker, the quality of the randomness is also improved. So here I used the feature models problem because it's one of the problems where we are able to count, to enumerate all the solutions because there are few of them. We need to have small problems because the p-value has to be computed on a large number of samples and more samples than the total number of solutions. That's why we use the feature models. So this graph shows that increasing the number of variables improves the randomness. Now we want also to see the impact of the pivot, kappa. So here I'm using the on-call string problem with the constraint that the objective is less than 1. Because it's an optimization problem, we turn it into a satisfaction problem. So here we see that first, random Vardom is still as lower quality of randomness than my approach, and when increasing the pivot, the value kappa, we are improving the randomness. This is very easy to understand because in the extremal case, you will have kappa which is bigger than the total number of solutions, and in this case it's just you enumerate all the solutions in the first step and then you return a random solutions which is the perfect sampling. But even when you don't enumerate more than the total number of solutions, you still have an improvement of the randomness. So increasing the pivot improves the randomness. Now the impact of the probability. So here we still see that random Vardom has a lower quality of randomness than my approach, and we don't see any clear impact of changing the probability in the quality of the randomness. So the probability to add a tuple in the tables does not have a clear impact on the quality of the randomness. Here I was using again the on-call string problem with a bigger bigger constraint on the objective, which changes the number of solutions. Last, for the quality of randomness, we tested on the n-queen problems, and here we see that random Vardom still tends to 0, the p-value still tends to 0, but in our approach it tends to 1, so for the last two parameters, the red and purple lines, and it means that the sampling is uniform. So even if there is no theoretical guarantees, in practice on some problems the sampling is uniform. This is probably due to the structure of the n-queens problem. Here it was on the 9 queens, and this problem is very structured with a lot of symmetries. That's why we have this uniformity here. Now we also want to evaluate the running time of our approach. So let's focus on the green heat map. So the darker the green, the longer it took to sample one solution. So here we see that when we are increasing the number of variables, we are increasing the running time. This is easy to understand because when you are increasing the number of variables, you are increasing exponentially the number of tuples in the tables that you generate. So that will exponentially increase the running time just to generate tables. And the other property we can see here is that for the probability, when reducing the probability, reduces the running time. And this also is easy to understand because when you reduce the probability, it means that you will have less tuples in the tables, so it will be faster to propagate, and also it will reduce the solution space faster, so you will have less steps to achieve to a solution set less than kappa. And then the impact of the pivot on the running time is very unclear. It depends on the other parameters, so we can't extract a clear rule of thumb for the impact of the pivot. So what you should remember is that reducing the number of variables reduces the running time, and reducing the probability reduces the running time. Now let's compare to random random. So in the second column, I gave the running time for random random on 2 problems and on the 12 queens problems, and table samplings with different parameters. And in the end, I give the ratio. So if the ratio is less than 1, then table sampling is faster, and if it's bigger than 1, then random random is faster. So what we see is that on on-call rostering problem, we are up to 3 times faster than random random, but on the other problems, we are slower by a decent factor. Here it's at most factor 7. And to understand these 2 differences, we have to understand that these 2 problems are very different because the 12 queens has a lot of solutions and on-call rostering is a very sparse problem. And why we perform very well on on-call rostering is because we keep the search strategy defined by default by the solver. So in Choco, it's DOM over WDEG and last conflicts. But if we use random random, you erase this search strategy and you just search at random. And the problem on on-call rostering is that you will often fail if you search at random because there is very few solutions. So random random makes a lot of mistakes, and that's why we perform better on this problem. So just a summary. We are looking at the impact of increasing a parameter on the quality of randomness and on the running time. So the number of variables, when you increase it, you will improve the randomness, but you will also increase the running time. Now the pivot, when you increase it, you will improve the randomness and you won't have a clear impact on the running time. And the probability, when you increase it, you have no impact on the quality of randomness and you have a bad impact on the running time, meaning that you can choose a small probability and you will have a lower running time. To conclude, I showed you a sampling algorithm that can use a solver as a black box as long as it implements the table constraints, and I showed that it improves compared to the strategy random random. And there is a lot of ideas for the future, notably to use other constraints instead of table constraints. Also to have specific applications to optimization problems. And we could also analyze the structure of the problem, like in counting, for example, to have a better randomness. So thank you for your attention, and I will be answering questions if you have any. So I leave this hiring advertisement. Thank you very much.